Today I'm going to give a presentation that focuses on a methodology we've developed for estimating the historical range of variability in fire-adapted forests. Because we usually lack data on historical conditions, we often use models to estimate them. And this is a graphical representation of a state in transition model that's used to do that. So you can see in this particular ponderosa pine ecosystem, there are 5 states or seral stages defined, starting with an early post-disturbance phase in the middle. On the left side, you see a mid and a late open phase, and on the right, a mid and a late closed stage. And so between those phases, there are successional pathways, as represented by these black arrows, and then orange arrows to represent disturbance pathways, in this case the dominant fire pathways. By assigning probabilities to these transitions, we can run the model out over time and estimate an average reference condition. So this average reference condition shows the percent of the landscape that we would expect on average in these various states. And in this particular model, you would expect most of the landscape to be dominated by the mid and the late open classes. So that mean is often used as a benchmark for assessing departure. And this is the methodology, or similar to the method used for fire regime condition class and implemented in the LANDFIRE program. So here you can see in orange a reference condition for your various seral stages, and it shows what percent of the landscape those classes occupy. You can compare that to a current condition, which we can get from map, and then the difference between those is your departure. Well, we know that there's some variation around that mean, and it would be useful to estimate that to improve our departure estimates and to give managers more information about these ecosystems and potentially greater flexibility in their management options. Various approaches have been tried to estimate this range of variability. Some folks have taken that modeled mean and just added a set amount, say plus or minus 10%, and defined that as their range. Others have used stochastic model variation to estimate the range. And then there are a host of other ways that people have gone about doing this. Well, the LANDFIRE program created over 1,000 reference condition models for every vegetation type it maps in the country. And as we went around the country making these models, we were asked time and again, how could we use these models to estimate HRV? So what we tried to do here was, one, develop an approach that used information found in that LANDFIRE model set to develop or estimate a historical range of variability, and then also to create a method that did not require extensive modeling expertise or additional ancillary data. So we used the Dry-Mesic mixed conifer forest as a test case in Oregon and Washington, and you can see its distribution here in dark green and the entire range of forests in the 2 states in light green. Because the dominant disturbance in the mixed conifer biophysical setting was fire, we chose a modeling approach that varied the fire return interval in order to estimate the range of variability for each class in the model. So from the model documentation, we had a modeled mean value, and that's shown in red on each of these graphs. So it's a modeled mean for replacement, mixed, and surface fire, and that was a product from the model. And then in purple, you see an estimated min, and in blue, the estimated max. And those were values that did not come out of the model, but they were found in the model documentation. And so these were numbers estimated by our modelers based on data or their expert judgment. The LANDFIRE models did not provide any information about fire frequency distribution, and so we had to estimate that. What we did was we used a bell-shaped beta distribution, and we scaled it to have a mean value and the range between the min and the max values provided by the LANDFIRE model. This step of estimating the distribution was subjective, and this is an area where you could experiment if you had information to suggest that a different distribution would be more appropriate. With that information, We put the LANDFIRE model into the STSIM modeling platform for state and transition modeling. And the only change we made to the LANDFIRE model was to set it up so that for every simulation, the model sampled one fire return interval from those distributions I just showed. And we ran the model out over 1,000 time steps, and these are our results. So on the x-axis, you can see our state classes, including an uncharacteristic state on the far right. And then on the y-axis, you see the percent of the landscape. The orange line is the LANDFIRE mean reference condition, and the gray box around that represents plus or minus 1 standard deviation from our HRV simulation. The black lines show the min and max from that HRV simulation, and the red dot is the LANDFIRE current condition, which I calculated from the LANDFIRE 2010 data. So one of the things that jumps out first is that some classes vary more than others. So for example, you can see there's more variability in the distribution of the early and the late open classes, and significantly less variability in that mid-closed state. You can also see that, well, the mid-open class is slightly overrepresented on the landscape today. It still falls well within our modeled range of variability, as opposed to the 2 late classes, which are significantly departed, not only significantly departed from the mean, but they fall well outside of that range that we simulated. So having this range of variability doesn't change the assessment that for this BPS, it's just departed, no matter how you look at it. But it does give you more information for evaluating the landscape and potentially developing management actions. So our modeling approach, like any other, has its strengths and weaknesses. I think one of its great strengths is that the data are available nationally. So we have one of these models for every ecosystem that we've mapped around the country. However, the information about the range, whether it's the range of variability in the fire return interval or some other disturbance, is going to vary from model to model. In this particular case, with the mixed conifer, it was a good test case because we had a min and a max value for all fire severity types, but that might not be the case in all systems. And then in systems where fire is not the dominant disturbance, you might need to come up with those values for different disturbances, for example, flooding in a riparian system. Another advantage of this method is that it's flexible. The assumptions are clear, and you can change them to meet your needs in different areas. But we don't overcome the fact that there's just still uncertainty about the fire distribution. We don't really know what that was. We do think, though, that this offers one way to estimate a reasonable approximation of what that range is. So we think we've put the R back in HRV. However, there's still uncertainty about the value of the historical range in the face of a changing climate. And so if you feel that the historical range is not valuable, you could change the model to represent a future or a desired range of variability.